This video is about translation software, and by that I mean the interpreters and compilers from AS. We're just going to look a little bit deeper into what compilers do. But let's start with a quick AS recap. So just remember that an interpreter takes source code, it translates one line of code at a time into object code and executes it, and it halts translation at the first error. The important thing about interpreters is that the user needs the translation software to run the program every time. In comparison, the compiler takes source code, it will translate the entire program in one go, not one line at a time. It then displays all errors, if there are errors, in a list on the screen. And the user can run the compiled code without translation software once it's been generated by the compiler. So if we look at the compilation process, we have source code, intermediate code, and object code. And in AS, you were talking about source code, and then something happened in the middle, and you ended up with object code. But now we're going to talk more about the front-end analysis, so the sort of cloud that's between source code and intermediate code, and then the back-end synthesis, which looks at improving the intermediate code and making sure that it's efficient as possible before object code is created. With your front-end analysis, it's going to be split into 4 different parts. So we have lexical analysis, syntax analysis, semantic analysis, and then finally code generation, and that generates the intermediate code. So with lexical analysis, it looks at the program source code and turns it into tokens. These tokens are then categorized into keywords, operators, or identifiers, etc. And we care about the identifiers because they're going to be stored in something called the symbol table. It's a bit like a dictionary. With syntax analysis, that's also known as parsing. It looks at how the program is constructed, or how each line of the program is constructed, and it turns it into something called a parse tree. So if we look at this example, this line of code is y equals 2 times x plus 4. And to turn it into a parse tree, which you'll see again in a future lesson, we can construct it this way. So it's the equal signs first and then y's on the left. And because there's more things on the right hand side, we have to have sort of separate parts to the tree. But that's a parse tree. Okay, we don't have to write one now, but you have to recognize it as a parse tree. Once we've got the parse tree, we do something called semantic analysis, which gives context to the parse tree itself. And we do that through looking at the scope of variables, checking that the variables have the correct type, and also checking that you're working within the bounds of an array. So here's an example. If we have int a equals value in quotes, that's obviously wrong. But the program won't know that until it reaches the semantic analysis part of compilation. But it looks and says, okay, there's an integer variable called a, and I'm going to assign this value to that integer variable. And this will fail semantic analysis because there's a type error. Okay. Other ways of looking into giving context to the parse tree is something called Backus-Naur form, and there's a separate video on that. The last part is code generation. Like I say, it's when the intermediate object code is produced, okay? And it happens prior to the back-end synthesis, which we're about to look at on the next page. So with back-end synthesis, it's really just about 2 things: error reporting and machine code generation. So what error reporting does is that if there are any errors encountered in syntax or semantic analysis, it's going to display that on the screen. With machine code generation, if there's no errors, it will optimize the intermediate code, so maybe improve execution time, and then generate the machine code, which is the final object code. Now there's different methods of optimization, and you can sort of fall down this rabbit hole of optimization techniques for compilers. But the main one we care about is the idea that we can simplify expressions so that they can be more efficiently evaluated by a processor. And I don't know if you remember that processors have registers. One of those registers is an internal stack. And so we're going to be looking into something called reverse Polish notation in a separate video, and that will show you how to turn a traditional expression, which is called an infix expression, into reverse Polish notation, which makes it easier for a processor to understand.